For Unit 10, we are going to be looking at exponential functions here. So to start off with, we need to complete the table and examine the patterns. So we already have 5 to the 5th, that's 3,125. 5 to the 4th is 625. 5 to the 3rd means 5 times 5 times 5, which would be 125. Then we have 5 squared, or 5 to the 2nd power, which is 25. 5 to the 1st power is 5. 5 to the 0 power is 1, and we'll talk about a 0 power later on here in this lesson. And then we move into negative exponents, and when we have negative exponents, that means we have a fraction. So 1 over 5 to the 1st, so that would be 1/5. And then 5 to the negative 2nd would be 1 over 5 to the 2nd, which would be 1/25. All right, so also the negative exponents, we could write those as a decimal as well, but I would prefer them as fractions. But 1/5 is 0.2, and 1/25 would be 400ths. So those are the decimal conversions for those. All right, for this example, we have to solve. 4 to the negative 2nd power would be 1 over 4 to the 2nd power, and 4 to the 2nd power is 16, so this is 1/16. So anytime you see a negative, we know we have to have a fraction answer. 3 to the negative 3rd is 1 over 3 to the 3rd power, and 3 times 3 times 3 would be 27. And then lastly over here, 2 to the negative 4th would be 1 over 2 to the 4th. 2 times 2 is 4, times 2 is 8, times 2 is 16. So 1 over 16 there as well. All right, here is the one I was talking about, the 0 power. Any non-zero number, so that means any number that's not 0, raised to the 0 power is 1. So for an example here, I have c to the 0 power equals 1, as long as c is not 0. So it can be -5, it can be a million, it could be 84, it could be anything. Raised to the 0 power, the answer is 1. So anytime you see that, it's automatically 1. All right, and then I just talked about this. Any non-zero number raised to a negative power is equal to 1 divided by the number raised to the opposite power. So we just talked about that. So this one, c to the negative n, is we see that negative exponent, so we automatically know we have to do 1 over, and then it would be c to the positive n exponent there. And of course, that is also when c is not 0. It does not work when c is 0. All right, exponential function is the successive output values that are related by a constant ratio. So this is our exponential function form, and where a, b, and x are real numbers, a can't be 0, b has to be greater than 0, and b also can't be 1. So the constant ratio is b. So lots of information there that we need to keep in mind. So example 1 says make a table for this function f of x equals 2 times 2/3 to the x power using the input values of x equals -2, -1, 0, 1, 2, and 3. Then graph the function using the ordered pairs from the table as a guide. So they're asking us to make a t-table with our x and y values, and they're telling us x is -2, -1, 0, 1, 2, and 3. So we have to plug them in to this formula. So 2 times 2/3 to the -2nd power. If I had to do this by hand, we already have a fraction raised to a negative exponent. So in order to solve that, we would flip the fraction, and flipping the fraction makes the exponent positive. And then we would have to square it. So 3 squared would be 9, and 2 squared would be 4. And then we would have to times that by 2. So 2 times 9 is 18, and then 1 times 4 is 4. 4 goes into 18 4 times. That takes us to 16, and with 2 left over, so 2 fourths. So 4.5 is our answer here. So if you had to do it by hand, you would flip that fraction, square both numbers, and then times it by 2. So this answer here is 4.5. Now, we have access to calculators, and we will be using those to figure out these answers here. So the next one I'm going to do is -1. When I type in -1, 2 times 2/3 to the -1st power, I get an answer of 3. And when I go back and change that to an exponent of 0, I get 2. And then when I change it to an exponent of 1, I get 1 1/3. And then I'm going to change it to an exponent of 2, and I get 8/9. And then an exponent of 3, me 16/27. So now we have to plot some of these points. Now, and I said some of these points because some of these are going to be pretty difficult to plot. So the first one, -2, 4.5. So I'm going to go over to -2, up 4.5. Then I'm going to go to -1 and up 3, over 0, up 2, over 1 and up 1 1/3, over 2 and up 8/9, and that is almost a 1, and then over 3 and up 16/27. That's going to be somewhere roughly in there. So we're going to estimate and try our best, but what you can kind of see is this is going downhill like this. So this is what an exponential function looks like. So somebody once said that they kind of remind them of hockey sticks. So they might go in this direction or they might go like this. So those are your two exponential function graphs that we're going to see. So example 2 says when a piece of paper is folded in half, the total thickness doubles. Suppose an unfolded piece of paper is 1/10 of a millimeter thick. Write an equation for the total thickness that's called T of n. So our equation is going to be T of n equals as a function of the number of folds n. Then use the function to determine the thickness of a paper after 5 folds and 8 folds. We talked about how exponential function was going to look like a times b to the x power. A is our starting thickness here in this case, which would be 0.1. B is what happens to it, and it says it doubles. So doubles means times 2, and x is how many times. So they asked us to find 5 folds and 8 folds. So we have 2 different answers. We have to do this twice. So I have to do 0.1 times 2 to the 5th, and then I have to do 0.1 times 2 to the 8th. So when I type that in my calculator, five folds would be 3.2, and we're talking about millimeters. And then if I fold that paper 8 times, I would get 25.6 millimeters thick. So notice how that jumped, only 3 more folds, and it went from 3.2 to 25.6. So exponential growth or decay, so it either can grow really fast or it can decay really fast. So you know that's when it's exponential, when you see that kind of growth or change, I guess. So example 3, the height, h of n, of a ball dropped and is an exponential function of the number of bounces n. On its first bounce, a certain ball reached a height of 15 inches. On its second bounce, the ball reached a height of 7.5 inches. Write an equation for the height of the ball in inches as a function of the number of bounces. So step 1, divide the successive function values or heights to find the constant ratio of b. So we are going to take this, the second bounce, which is 7.5, and divide it by 15. And when I do that, I get 0.5 or 1/2. Step 2 is to use the value of b and a known ordered pair to find the value of a. Well, what we know is the first bounce is equal to 15, and we know the second bounce is equal to 7.5. So we also know that the exponential function formula is a times b to the x power. So we know that the constant is 0.5. We figured that out in step 1. We also know after the first bounce, the height is 15. So the only thing we're missing is a. Where did it start? So we can do 0.5 to the first power. That's going to leave us with 0.5. And then we have to solve for a. So I'm going to divide by 0.5 on both sides. So I get a is 15 divided by 1/2 is the same thing as timesing by 2. So a is 30. So our initial. And then it says write an equation for the function h of n. So we just figured out a was 30. We also figured out b was that 0.5. And then we have x. X is the number of bounces. So that can change. That's our going to stay a variable there.